Objective 12.2, Combinations. In Objective 12.2, we're going to use yet another method to count the number of ways an event can happen. We've had the counting principle, we've had permutations, and now we're adding the method called combinations. So what is a combination? It is a selection of R objects from a group of N objects where order is not important. So this makes it different from permutations. In permutations, it does make a difference what order your objects will be in as to whether to count it as a result. In combinations, a mixed up order of the same objects all counts as one result. So the order does not make any difference. It is not important. The notation for this looks similar to permutations, but instead of a P here in the middle, we have a C to represent that we're doing a combination. And then we have our n factorial on top. We still have our n minus r factorial on the bottom, but then we also have just r factorial on the bottom. And this is technically being multiplied together down here. Okay. So it's n minus r factorial times n factorial in our denominator. So we read this, the combination of n objects taken r at a time. That means we have n objects in total. We want to choose r of them, and the order doesn't matter. In any order, it all counts as the same result. Now the toughest part about remembering this compared to permutations is really remembering which one should also have r factorial in it. And so one way you can think about it is that if you go back to our skier example from the permutation lesson, we said that if Amy wins gold, Bob wins silver, and Carl wins bronze, that would be considered a different result than if Bob won gold, Carl won silver, and Amy won bronze. So in permutations, the order would matter. Therefore, even though it's the same three people, they would count as different results depending on that order, and so we would end up with more possibilities. In a combination, because Amy, Bob, and Carl would count as one result regardless of what order they were in, we don't need as many different possibilities. And so in order to get fewer possibilities, you can think about having to divide by more stuff. If we divide by more, we're going to get fewer as a result. Okay, so that might be a way that you can remember that combinations, where order does not matter, should have fewer possibilities and therefore needs to be divided by more. So it needs to have the r factorial as well as the n minus r factorial. All right, so let's actually put this to work. So here's an example where we're talking about a standard deck of 52 cards, where we have 4 suits, the clubs, the diamonds, the hearts, and the spades. And in each suit we have 13 different cards, from ace up to the face cards jack, queen, and king. So my first question is, how many different 5-card hands are possible? Well, in a 5-card hand, does it matter what order the cards are dealt to you in? Usually the answer is no. So if the order does not matter, then we want to be looking at a combination. So this is a combination where we have 52 total cards, and we want to take 5 of them. So this is what we set up. Here's our 52 taken 5 at a time. That means 52 factorial on top. 52 minus 5 is 47 factorial, as well as the 5 factorial on the bottom. And if we work all of that out, we would end up with 2,598,960 different 5-card hands that could be dealt from this 52-card deck. Okay. Another question dealing with our cards here. So let's say you ask each of your 3 friends to draw a card from a full deck. In how many ways can the cards be drawn? So does order matter in this case? In a sense, yes, it does. Because if your 3 friends draw the same 3 cards, but different friends have different cards, then that's a different result. For example, let's go back to Amy, Bob, and Carl. If Amy draws a 2 of hearts, Bob draws a 3 of hearts, and Carl draws a 4 of hearts, that's one result. But if Amy draws the 3 of hearts, Bob draws the 4 of hearts, and Carl draws the 2 of hearts, even though they're the same 3 cards, that to me is a different result because different people got different cards. So this would be a case where order does matter. And therefore, to set it up, we need to go back to permutations. So 52 cards taken 3 at a time now, because we just have 3 friends drawing, is going to be set up as 52 factorial over 49 factorial, that's the 52 minus 3, and that's going to be equal to 132,600 different possible ways that your 3 friends could draw a card each. Okay, so this is the big difference. This is what tells you whether you should be using a combination or a permutation. Does the order make a difference? If your answer is no, then you use a combination to figure things out. If your answer is yes, then you need to use a permutation. Let's take a look at one more card example here. Now I want to know how many 5-card hands would contain 5 cards of all the same suit. So it's not just a flat out choose 5 from anything. We want to know if they're all the same suit. So in this case, we're actually going to combine what we know about counting principle with what we're doing here with combinations. And so we set up the counting principle by looking at the 2 things we're trying to do. We're trying to get 5-card hand, but we're also trying to get them all of the same suit. So I've made a blank here to represent the suit that we get, and then a blank here to represent the 5-card hand that we get. So in the suit, we have 4 suits in our deck of cards, and we want to choose one of them. Does it matter what order? Well, since we're only choosing one, that's kind of a weird question, but no, it doesn't matter what order. So that means we have a combination of 4 suits taken one at a time to represent possible ways of getting the suit. Then within that suit, we want to get 5 cards. Within any one suit, we have 13 different cards for choices. Does it matter what order we get the 5 cards in? No. So we're again going to use combinations, but this time we're choosing only from the 13, not from the whole 32. We're choosing 13 from 13 cards that all have the same suit, and we want to choose 5 of them. And so that's what we're going to work out. The combination of 4 taken one at a time would be this. The combination of 13 taken 5 at a time would be this. And that works out to be 5,148 different possible ways to get 5 cards all of the same suit. Okay, so look for this. There's going to be different situations now where we can combine things from last lesson along with things from this lesson, like using the counting principle along with combinations to help us figure out how many ways to get 5 cards all of the same suit. All right, let's take a look at a different example now. In this case, we're talking about a restaurant that serves omelets. And so you can see their sign there about how they charge for the omelets. An omelet itself is $3, and then you add 50 cents for every ingredient that you add. And they have a vegetarian list of ingredients and a meat list of ingredients. Okay, so in part A, it says, suppose you want exactly 2 vegetarian and 1 meat ingredient in your omelet. So maybe you want cheese and mushrooms and sausage in your omelet. Okay, but the question is, how many different ways can you order that omelet? So cheese, mushroom, and sausage is one way, but how many different omelets could you order that would have exactly 2 vegetarian options and 1 meat option? So we set things up again using a combination with a counting principle. Your first choice has to do with your vegetarian ingredients. So there are 6 vegetarian options, 1, 2, 3, 4, 5, 6, and you are choosing 2 of them. So your first combination is 6 taken 2 at a time. Then along with that, you also want 1 meat ingredient. So for the meat option, you have 4 choices, ham, bacon, sausage, and steak, and you're choosing 1 of those. So you have the combination 4 taken 1 at a time. We're multiplying these 2 together because both of these choices are going to be in the same omelet. So just like with our sandwich example last lesson, if we're taking the meat times the bread, well, we're taking the vegetarian times the meat here for the omelet. Okay, so when we work things out, here's our setup for our combination of 6 taken 2 at a time. Here's the setup for 4 taken 1 at a time. And when we work this out, we're going to take 15 times 4, which is going to give us 60. So there's 60 different omelets you could order that would have exactly 2 vegetarian ingredients and 1 meat ingredient. Now what about part B? It says suppose you can afford at most 3 ingredients in your omelet. Now how many different types of omelets can you order? Well, we first have to interpret this at most 3 ingredients part. What that's telling me is that I could order an omelet with no ingredients, 1 ingredient, 2 ingredients, or 3 ingredients. All of those are possibilities. But it's not all the same omelet that's going to have those in it. So this time, instead of multiplying my combinations together, I'm simply going to add all of those possibilities together. So I have 10 total ingredients to choose from. One possibility is that I don't choose anything. So 10 taken 0 at a time. Now, in case you haven't realized this yet, when you take 0 factorial, it's still just equal to 1. So when you're working this out, keep that in mind, that 0 factorial will just be 1. So this is our number of combinations of having no ingredients. Makes sense that that would just probably be excuse me, a 1 as an answer. Okay, so that's what we get here. Then I have the combination of 10 ingredients taken 1 at a time. Well, if I just want 1 ingredient, there's 10 different choices, so that makes sense that I would get 10 from that. Then I can take my 10 ingredients and choose 2 of them in whatever order. So that gives me 45 different possibilities. And then 10 ingredients chosen 3 at a time would give me 120 possibilities. So when I add all of those possibilities up, I end up with a total number of 176 different omelets. Okay, so we have these 2 different situations going on here, where in one case we multiplied our combinations, and in another case we added them. And really, I think the way to determine which one to do is whether you're talking about 2 things happening within the same situation, so like 2 choices within the same omelet, or if you're talking about separate different omelets. Okay, that hopefully can help you decipher in your homework whether we should be multiplying or whether we should be adding. We're talking about different situations of omelets, having 0 ingredients, 1 ingredient, 2 ingredient, 3 ingredient, then we're just going to add those combinations together. We're talking about choices within one omelet, then we're going to multiply those choices together. Okay? Alright, so that's the information you need for combinations. You should now go to the Mentor Mob if you're not there, or if you are there, just go to your next step and take the 12.2 quick quiz. Once you've taken that quick quiz and submitted your answers, then you can move on to working on your 12.2 practice. And once you've completed this entire 12.2 objective, make sure you show it to me so that we can check it off. That's it for today. We'll see you next class.